Okay, so this summary frame goes along with your packet that you completed the other day in class. These few questions go along with pages 457 through 460 in your textbook. So, in our own words, describe what it means for a sequence of partial sums to converge. Provide a unique example. I think in my own words, I would say, for a sequence of partial sums to converge, as we continue to add terms, the terms we add approach a value of 0. So here's a quick example. I could take 1 and add 0.1 and add 0.001 and add 0.0001. So this is a geometric series with a common ratio of 0.1. And I notice as I continue to add terms that the terms are getting smaller and smaller, approaching 0. This will converge. We also learned in our notes that we can figure out what value it converges to by taking a1 over 1 minus r. So in this case, what value do we converge to? 1 over 1 minus, the common ratio is 0.1. So this would be 1 over 0.9. And let's run that calculation on our calculator because I'm not exactly sure. 1 over 0.9 is 1.111. So this converges to 1.111. Moving on to question 2. Explain a situation in which a partial sum would diverge. Provide a unique example. For a sequence to diverge, the terms we add continue to grow without bound. So there's a big difference between the terms we're adding when we're converging versus when we are diverging. So I can have the sum, maybe something that looks like this: 1 plus pi over 2, which is approximately 1.57, plus pi over 2 squared, 2.467, plus pi over 2 cubed, 6.088, and so on. So we clearly see that as we continue to add terms, we grow without bound. So now as we approach question 3, I can kind of study my example from number 1. In an infinite series, if I'm adding up the terms and I look at many of them, if I say that it converges, then why must the limit of the kth term equal 0? Again, I turn your attention to the first example. If you consider this term that I'm pointing to be the kth term, I can see that if I took the limit, it is definitely approaching 0. So for a convergent series, the limit of a sub k as x approaches infinity must equal 0 in order for the sum of the terms to approach a single value. We learned from our first lesson that a geometric series converges when the absolute value of the common ratio is less than 1, or minus 1 is less than r is less than 1. If Instead of r, we're using x. The absolute value of x has to be less than 1. We say that minus 1 is less than x, less than 1. We also call this the interval of convergence. I'm also going to add one more thing. If I were to plot this on a number line, here's minus 1 and 1. 0's right in the middle. There's another term called the radius of convergence. This is something we're going to have to learn about. It's a very simple thing to find. All you have to do is go draw your interval of convergence. So here's my interval. I go to the center and I draw a ray that goes from the center to one of the endpoints, and this length from the center to the end is the radius of convergence. So for a basic function with this interval of convergence, we'd say the radius of convergence is 1. Finally, provide an example of a geometric series that converges and one that diverges. A geometric series that converges would be a series that looks like something like this: 1 plus a half plus a fourth plus an eighth, and so on, where the common ratio is a half. And using our example from above, an example of a geometric series that diverges would be maybe something like 1 plus pi over 2 plus pi over 2 squared plus pi over 2 cubed. And we would say that the common ratio is pi over 2, and we know this as a decimal to be about 1.57. And notice it's bigger than 1, and that's why it diverges.